You remember, in a previous episode, we created an assembly file. Next, we're going to assemble our code into a binary file. Now, isn't that called compiling? Using a compiler? Well, you could use the term interchangeably. But if you want to get technical, we're going to be working in a lower level programming language. So we will be assembling our code. So hopefully, if you've been following this series, you've installed NASM and set up a path in the environment variables. We'll also want a hex editor. I'll be using HXD hex editor in this case. I would like to give a moment of homage and tribute to Nick Blundell, without whose lower level programming series on YouTube really helped shed some light on this obscure topic, and without whom much of this might not have been possible. My hero. Leave it to a British chap, huh, to put lower level programming into proper English, isn't it? So starting out, I'm going to right click on the Explorer here. That brings up our favorites. We're going to go to the assembly folder there. There is our test file, which we've set up to be recognized by Notepad++. Nice, by default. Um, as you know, we can Alt P, and there you can see the contents of the file, great big zero. Alt P back out of there. I'm going to put this over here for a sec. And then I want to left click here where there's like these foldery looking things. If I left click, it turns into a path that's already highlighted. I can Control C, and then I'm going to head over to the command prompt there and change directories. I can just right click in the window and it automatically pastes it. Nice, enter. There, so now I'm there. Okay, so first thing we want to do is make sure that NASM is installed and running. We can just go NASM and check the version number, and there it tells us the latest version is installed, ready to go, and is recognized from the command line because we have set it up to do so. Wonderful. So without further ado, let's call NASM. Type of file will be a binary. The name of the output, whoops, sorry, binary. We'll type T tab to find the file. Name of output will be binary dot binary. How's that? Just to be redundant, say the same thing two different ways, if you know what I'm saying. If you catch my double entendre. And Bob's your uncle. There we go. We have successfully just created our binary file. There. Um, there it is. Okay, so I mean, and normally you could try to double click on that, and it would just open Notepad and show you nothing because that's what we wrote into it, nothing. You couldn't look at it, view it from the command prompt either. No, you need a special application which we have installed and set it up to be our default reader, which is HXD, which can read binary files. Um, so we can call that from right down here at our command prompt now. Sorry, let me go CD back to where I was, and there. We just want to go look at B tab, enter. There, and there is our hex editor. As you can see, we wrote a 0 in there, and what we've actually written is 0, 0, 0, 0, 0, 0, 0, 0, 8 zeros, or a byte, 8 bits. So let's see, this much is a nibble, and this much is a byte. Now, I've never heard of anybody working in nibbles, but that's your computer terminology. So 1 byte of information here expressed as hexadecimal, and it's also a 0 there, right? So I could go in here right in our hex editor and change this to a 1 and hit enter. It updates it over here as well. Now it's in red, indicating that it hasn't been saved. Okay, or I could change this one to say a 9. This is the decimal equivalent. So here it's in binary. And as you can see, our binary representation is 8 plus 1 equals 9 in binary. As you know, it's 1, 2, 4, 8, 16, 32, 64, 128 places in in binary. So that's the value 9. Same in hexadecimal. Now what if I change this to 10? There. There's 10 in binary. Oh, well, what happened over here? This turned into an A. See, that's because we are looking in hexadecimal. Fortunately, we have a reference right here in front of us, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, because it's 16 places, hexadecimal. This being OF being 15, and so counting 0, 16 places in hexadecimal. Power of 16, binary being power of 2, decimal, power of 10. Just different ways of expressing the same value, but it's all ones and zeros to the computer, you know. It's basically a bunch of electronic switches, and it's saying if this switch is turned on and this switch is turned on, then do something, depending on the context in which the value is used. So I could go over here now. Here we have 0A, and what if I type 0F? Okay, now everything disappears over here, but I think if I click, let me click at the beginning of the line. Yeah, good. And there you go. There's the value expressed as binary and decimal value. Okay, so now what if let me change this to FF? Enter, and you click there. Okay, here we have a positive value of 255. As you can see, FF is the maximum that you can hold in there. It's all filled up with ones, 255. But what's going on over here? This is turned to a negative value. Okay, so this same value could be used more than one different way to the computer or to the programmer even. Here we are using a signed integer. And here, an unsigned integer. What's that mean? Well, you have a limited amount of space that you can store in 1 byte. 255, counting 0, 256 places, right? So if you wanted to deal in negative numbers, and how do you do about that? Well, basically, you make half of this positive and the other half negative. So essentially, this leading value in binary, if we're dealing in signed integers, tells it whether it's positive or negative. If this is a 1, the value will be negative, and if it's a 0, the value will be positive, you see. So what happens here, I got 127. I'm going to change that to 128. You see, it flipped over to a 1 here, and this went negative now, negative 128. See, so now if I add one more to that, 129, you see, it added one more to negative 128. You see, negative 128 plus 1 is negative 127, you see. So the way that works out, let me go all the way up to, what would be like 254, 1, 1, 1, 1, 1, 1, 1, 0, right? See, and now we've climbed all the way up to a negative 2. See, we'll go 255. When we're full up, that's as high as we can go. In this value here, it's negative 1 in signed integer value. Now, what happens if we take negative 1 and add a 1 to it? What do we get? Okay, so what happens inside the computer is this value here should now roll over, and the 1 will go off the screen somewhere over here. It doesn't actually disappear. It's written to a flag, so you can check the value later. That's another topic. But when this rolls over, if we add one more to this, 256, whoa, it won't let us want to add one more to this. But if we do, what happens is you get an overflow. 3, 4, 1, 2, 3, 4. The negative 1 becomes 0. See? So adding 1 results in an overflow, but it is the correct value when you're dealing in positive and negative, working in signed integers. You know, alternatively, if you're working in unsigned, then you have all positive values except for zero, unless you consider zero a positive value, right? Okay, I'm not spending too much time explaining all that. Let's, what else can we do here? Okay, so we can take a look at our file now for a moment. Save changes. No, I'm good on that. Um, so we can do that from the command line here. I'll just go T tab for test, and it launches Notepad. Some weirdness there. There, all fixed. DB0. We wrote a zero in there, right? I can write a lot of zeros. I could write another one. I could go to another line and do DB0 again, like that, you know. But another shortcut, since we're calling the same command here twice in a row, I could just comma there, db0, db0. Let me save that. Go over here to the command line. If I up arrow a few times, no, oh, I have to call NASM again from a new window. NAS. Oh, hang on here. Let me show you another trick real quick. NASM minus F binary T tab minus O. I can, oops, hang on. Minus O. I can just type B tab because the name's already in there and it finds it. Hit enter and overwrite. Okay, that's a bit of typing. You know, maybe I don't want to do that again next time. Our binary file is updated, but just let me pause here for a second. What I want to do is highlight this and Control C. I'm going to copy it. And then down here, I'm going to go put it into a text file. I'm going to go echo space, and you can right click to paste. That's handy. And we're going to space, put it in a new file. Whoops, hang on. Called snippets.txt. You can watch over here when I hit enter, and there's our little snippet, right? So what's handy about that is if you're compiling from the assembling from the command line now, I could just, as you know, enter type s for name of file, tab, and there's our shortcuts, list of shortcuts. I only have one in there at the moment, but now if I want that shortcut, I can just highlight it, hit enter, it's copied into memory, and then right click over here, it's pasted, and hit enter, and it will compile the binary file, which we've already done, but it overwrote it with the same thing. Great. Another cool trick. Let me show you this. If you start underneath here and then drag up, and then I'm going to Control C, and then if I right click, observe that it typed the command and executed it all in one fell swoop, because when I copied it, I also copied the return. Ah, handy little trick, right? Okay, so let's see, what else can we do here? Wait, get this out of the way for a second. I don't want it to be full screen, thank you. Let me look at this again in our binary file again real quick. B tab, all set up to be recognized by our hex editor. There, as you can see, we wrote 2 zeros in there. There's our 2 zeros. You see, what we've actually written is 0, 0, 0, 0, 0, 0, 0, 0, and then the same thing in there. 2 bytes, right, of 8 bits each. Okay, so I could also, that's because we've written our value in decimal here. You know, if I said 4, you know, that's assumed to be a decimal value. I could also write in binary. You know, I could just go 1, 2, 3, 4, 5, 6, 7, like that. B for binary, right? And I'm going to save that. We'll head over here. If I go up arrow, there's NASM. Go down arrow. There's our binary, and there's the 1 that we wrote in there in binary language. Okay. So I could also, here, let me go, I'm going to write a word, a data word there. So let me copy this bit, Control C, Control V, Control V. So a word being twice as much. It's going to be a binary value that is 16 bytes long. Okay, let me just put that in there, save it, head on over here, up arrow twice, enter, down arrow once, and there is our word expressed as 2 bytes, but it is a 16-bit value, a single number, expressed as a lower byte and an upper byte. Okay, so talk about that a bit here. So what here I put a value of 1 in the lower byte and another value of 1. What happens if I change this value to 2 in binary instead? 1, 2, 3, 4, 5, 6, 8. Let's save that. I'm going to head over here, compile it, look at it. Okay, so now this is very interesting here. Observe that we have written a value of 1 and 2, and what we got back is 2, 1. Okay, so what's up with that? Well, the reason for that is it's hardware based, essentially. It's due to the actual processor in your computer uses a little endian system. And what does that mean? Well, basically it means if you put in a 1 and 2, you get back 2, 1. It's backwards. Why is that? Well, Motorola had a chip back in the early days which worked normally. It was known as, we call it big endian today. It was, you put a 1 and a 2 in there, you get back a 1 and a 2. Okay, straightforward. And then Intel wanted to go into the business, right? So, it's like, well, since Motorola was one of their business associates, they can't just go start making chips the same way, they might get sued. So what you do is, for all I know, this could be the origin of the term reverse engineering, because when Intel made their chip just exactly like Motorola's, only theirs was in reverse, you see. There, no patent infringement there. I don't know if you've heard of the movie Pirates of the Silicon Valley, but there you go. That's America for you. So then IBM came out with their first computer, and of course, IBM owned 20% of Intel at one point. I don't know. Then they underpriced some of history's best computers right out of business. So today, unfortunately for us, the bass-ackwards chip is the de facto industry standards, right? And the common sense chip is pretty much a thing of the past. Another of many stumbling blocks due to piracy and endless obstacles from layers of legacy in the Intel x86 architecture. In fact, the next video, we'll be building a simple bootloader to overcome yet another built-in hardware legacy. The fun never ends here, folks. Another thing I wanted to show you, I'm going to just delete all this. Oh, and it asked me, do we want to change the file size? We're going to be doing that a lot, so don't bother me with that again. I can go up here to Edit, Insert Bytes, and 0 bytes. Now, how about 512 bytes random there? And this is really interesting too. I don't know if you've ever you're in a text editor and you try to open a program and you see something that looks like this, a bunch of garble. And I'm like, whoa, what is that? Well, now you know. What you're seeing is a text representation of actual code, you see. So here, this is kind of interesting. Look at this value here. There's the character U, represented by the value 55. Okay, U55. That's interesting. I'm just gonna undo. Let me just set all this back to 0 if I can. Backspace. Backspace, backspace, 0, save. I didn't really need to do that, but okay. So what did I say? U. Yeah, I'm gonna go back and make this a data byte. Watch this. Oop, U. Okay. I'll save that. We'll go over here, compile it, look at it, and there you go. The value, it's not 55, 55 in hex, the actual value of 85. And that, interesting. We'll be using that a bit later. Like here, it's one, oh, this is fun. 1010101010. If I changed this to a 0, we get the answer to life, the universe, and everything, right? Hang on, let me go. That's 42. Yeah, 101010. Right? Now you know. Um, so let me just set this back to 0 again. What's my, whoops. You got to highlight the whole, let me just hit backspace to enter, delete it completely, hit 0 there. I'm good. I'm just going to save that. Okay, and we're back to our big 0 again. What's my fascination with zeros? Well, stick around. In our next exciting episode, we'll be writing a whole lot of nothing, so stay tuned.